Good morning, everybody. Thank you, Ed. And yeah, so my name is Brandon Satrom. Just a little bit about myself. I have been in technology for over 18 years, almost 19 years. I'm a rookie, yeah. Just starting out at this whole thing. I have spent most of my career actually in the software side, so running software teams, working as a developer in the early part of my career, still doing development, something I've never been able to get away from fully. My day job is running our developer relations program at Gartner. I've been doing that since February. I'll talk a little bit about who we are in a bit. My evening job, my weekend job, my second job is actually I run a STEM education startup called Carrot Pants Studio. So we actually primarily produce learning resources to get kids excited about electronics, specifically in technology. We primarily do that through storytelling. So we have actually produced a couple of books and kits designed to get kids excited about electronics. So shameless plug, you can check that out at carrotpantstudios.com if you're interested. We've done 2 successful Kickstarter campaigns and I'm retired from Kickstarter forever now after doing that.
Say the name of it again.
It's carrotpantstudios.com. If you ask me afterwards, I'll tell you the story behind the name. But I'm not here to talk about that. I'm actually here to talk about Particle, and specifically to talk about our journey on the Internet of Things, extending all the way back to if this is going to work. Oh, come on. I might use yours after all. The battery dies. Just in the most inopportune times. Extending all the way back to 1926, when visionaries such as Nikola Tesla actually envisioned a future where we would live in the world that we live in today. I mean, it's fascinating to look at this quote from Tesla, and while his perception of wireless transfer of electricity not quite coming to fruition yet in the way that he has imagined, it's impressive that people like Tesla actually anticipated that we would live in a world where we had devices that we could carry in our pockets, where we had this huge brain connected the world together. And it's really quite fascinating to think that he was right about that, but that he actually predicted the world we're living in today. We're living in this amazing, idealized future. You know, a lot of our attention in technology over the course of the last 30 or 40 years has been on computing in general, right? We started with our focus from the 60s to the early 2000s on this idea of making personal computing ubiquitous. First, through the internet, through personal computers, through the internet, and then finally on mobile. But a lot of our attention, especially those of us in the room and the folks that we associate with day in and day out, has been on this idea of the Internet of Things, not just adding personal computers, but adding connectivity to everything around us. And so it's inevitable that as more and more of our attention, and especially more and more of the tech press's attention, started to focus on this idea of the Internet of Things, that we started talking not about millions and a few billion devices, but now 36 billion of devices, or if you listen to some analysts, trillions of devices actually connected to the internet. And as a result, trillions of dollars of opportunity. This is why most people are interested in this topic to begin with, because there's a whole lot of financial opportunity supposedly in this space as well. But those of us that are in this space are also very well versed that not only does this idea of the Internet of Things have a lot of promise, but it has had its share of pitfalls and its share of challenges as well. Because I feel like, from the consumer standpoint, instead of this glorious world of connected devices that improve our lives, what we're living with today is connected devices that lose their connections and start working against us. A lot of the bad press about the Internet of Things tends to be focused on the smart home, partly because it's quite visible, but these are problems that pervade in a lot of parts of the industry. Or we have devices that need to update their firmware at the worst possible time. Or, and this one just completely boggles my mind, a social media company that shall remain nameless that currently has very low consumer confidence, that around the time of their lowest point in popularity, they actually released a device that literally follows you around the room. And I'm just going to leave it at that. I can't say much more about it. Or, this is where I love things like computer vision. We have security devices with facial detection technology that is so good that wearing a Batman t-shirt just might result in you being locked out of your own home. I think where we are, and And so then there's also this challenge with the word smart. When we talk about smart technology, smart cities, smart homes, what we tend to mean is that we've used intelligence as a way to improve our lives. But I think for a lot of people, a lot of consumers in this space, they perceive the word smart to mean companies that have used intelligence to better sell us products because they're selling data about us. And that's the world that we're in. So I'm sure many of you are familiar with the ever-present Gartner hype cycle. When they talk about new technologies, they map technology trends on this very common cycle of interesting adoption, of a peak of expectations, a trough of disillusionment, before finally that technology moves into a slope of enlightenment and plateau of productivity. Every emerging technology that becomes accepted largely follows this path. Follows it at different speeds, but it tends to follow that path. Some technologies reach certain phases before they become accepted, and they just disappear they fall off the trough altogether. According to Gartner and others, IoT actually is here today. It's kind of crazy to think that from a public perception standpoint, many analysts predict that it's going to get worse before it gets better in the minds of many in the public. You can choose to agree or disagree with that, but when I talk to a lot of people, I talk to developers, I talk to executives really all over the country and all over the world, and I hear these kinds of things. I hear people that see the promise in the future but are still struggling to connect the silly things that we talk about when it comes to the IoT, where we're putting Wi-Fi chips in everything, like LED dog vests, and that actually is a product if you want to look it up, to actually connecting farms in rural areas and connecting our cities.
Who would think about that?
I know. There are lots of great examples of that, but in the mind of many people, what's happened is this quote that I had a friend, Particle actually did our first, excuse me, not getting emotional, I'm still recovering from a cough. Particle had our first developer conference in October this year in San Francisco, and a friend and former colleague of mine who came out to the conference actually said this to me after the fact. Until he had come to our conference, the phrase IoT had lost all meaning for him. It was just something he saw as a three-letter acronym. He understood the individual words that made up that acronym, but what it actually meant from a practical standpoint no longer had any meaning. And this is not all doom and gloom, but I think the reason why we've gotten to that place in many ways, I look at that, there's a number of reasons, but for me, the big three reasons I think why we've gotten into this place where the IoT is in the trough, or entering the trough of disillusionment, is because we're connecting things for the sake of connecting. A lot of vendors are putting Wi-Fi and cellular radios in things because they can, because it's the cheapest, most expedient way to get something on the internet. There are a lot of examples where IoT devices are poorly secured, if not secured at all, where IoT devices are being enlisted in botnet armies, and there are many examples of that. And then the final challenge is limited connectivity options. When it comes to the IoT, at least the state of the art today, and there are emerging things that I'll talk about, most people look at it as really three options. There's Wi-Fi, cellular, and Bluetooth. We'll talk about the limitations of those. And so I'm actually here this morning to share a relatively controversial opinion, and that is that I think to succeed, the IoT needs a little bit less internet in the future. And I'll explain exactly what I mean in that. This is a story in three parts.
Cowbell.
The first part, yes, we need more cowbells, more internet-connected cowbells. This story in three parts. I'll start by talking about mesh networking and why it matters. I'll talk about OpenThread specifically and some of the mesh networking standards that are out there. And then specifically I'll talk about how Particle makes mesh networking easy, why we got into this space, and why we think it's important. I already introduced myself a little bit. I'll share this again because I do developer relations work. I spend a lot of my time making animated GIFs. This is actually a part of the job description. But really what it comes down to is I build cool stuff for developers. I work with other developers building things. My goal is to help our developer community build even better products, and then also to make sure that we improve our products with developer feedback. And for those of you that are not familiar with Particle, we are an IoT platform company. We've been around for about 6 years. Particle actually, interesting backstory, started as a failed Kickstarter campaign for a connected lighting product back in the days where there was no Philips Hue light bulbs. after that failed Kickstarter campaign, the co-founders regrouped and decided that the real opportunity in this space was actually making Wi-Fi easy for developers. If many of you if you've ever done maker work or your own sort of prototyping at home or in your jobs, you know that the state of the art with Wi-Fi development and embedded systems 6 years ago, at least from a accessible maker standpoint, was you bought a $35 Arduino and a $65 Wi-Fi shield just to get that thing connected to the internet. So when Particle started, they were one of the first companies, and I think the first actually, that had a $30 Wi-Fi connected Arduino compatible product, drastically cheaper than what you could do elsewhere in the market that day. And that really kicked off their growth as a company. Now we have really an end-to-end full-stack IoT platform, all the way from hardware and firmware to Wi-Fi and cellular, and as I'll talk about in a few moments, mesh, to an IoT device cloud, and then web and mobile app SDKs. Our goal is to make it very easy for developers to prototype with our products and then eventually move to production with the same hardware, with the same firmware, with the same fleet management capabilities that we have in the product today. We have about 165,000 developers in our community. We have 8,500 companies that are working with Particle from over 170 countries and 500,000 devices that are online. Actually, I think it's closer to 750,000 as of today. This is from earlier this year. And one of the reasons, and this is one of the things that I love to talk about to developers really all over the world, and talk about people that are interested in the IoT, the reason why we're in this space. You know, you can look at where the IoT is in the hype cycle and think, well, I mean, obviously we see there's promise in the future, but how do you get past that? How do you get from that trough of disillusionment into the slope of enlightenment? And for us, and I think for all of you in this room as well, the thing that makes the difference with Particle is that we focus on solving real problems with our customers. It's not about silly connected dog vests, although sure those have a place, but it really is about our customers that are actually attempting to solve problems with connectivity that are interesting and unique and couldn't have been accomplished before when connectivity was too expensive, was inaccessible, or where it wasn't an option. We're enabling things with connectivity with backhaul to the cloud, with the use of cloud services, with machine learning and AI, and again, same things many of you in this room are doing that weren't possible 5, 10, and 15 years ago. And a lot of where we've gone as a company has really been driven by what our customers are asking for and where they're seeing problems that they need our help solving. I mentioned Wi-Fi. I mean, our goal as a company from the beginning was to make Wi-Fi easy for developers, and that's how we started. As we evolved in the first couple of years as a company, it became not only making Wi-Fi easy for development and prototyping, but making it easy for a company that was successful with a prototype to move to production. I'm sure that many of you that have done this in industrial settings see there's a very common thread that happens in the IoT space where people prototype with an Arduino or with a Raspberry Pi, and then when they're done they say, now I need to find my real hardware, and I need to find my real device. But what happens at that point is you are starting over from scratch. You have proven an idea, but now you're going to reprove it on brand new hardware and brand new infrastructure, and really with brand new problems. And so we have tried to really focus on helping our customers move from prototyping to production by having a dev kit that's breadboard friendly, but then moving to mass production modules that run the same device OS firmware without changes that can then be embedded on their custom PCBs and on their products. And this is how we started very early on. But we had customers, we noticed there were many customers that were starting to ask for, okay, now this is great, Wi-Fi is fantastic, I don't have a Wi-Fi hotspot where I am, out in the field or on the shop floor, I need cellular. And so a few years later we moved into cellular products. We introduced a product called the Electron, but we kept the same idea of having a breadboard friendly dev kit and then moving into modules that were easier to scale with. And so a lot of our enterprise customers, a few examples, or one key example we share a lot is Jacuzzi. So Jacuzzi uses a product like this. We have other companies that use cellular for asset tracking. It's a really common use case where customers use this board plus a GPS module.
Bless you.
Excuse me. Plus a GPS module to perform asset tracking on their fleet of devices, whether it's trucks or it's smaller assets, etc. And this has served many of our customers quite well. But as we have moved, as we've engaged with those customers over the last couple of years, we've been led down this path of introducing a new hardware option. Not a replacement for Wi-Fi and cellular, but in addition to Wi-Fi and cellular in the context of our mesh-capable hardware. So our third generation devices are not a replacement for what we have today, but an expansion via the use of Wi-Fi, cellular, and mesh boards, all of which can communicate in local networks. So I'll actually talk about that a little bit now, and why mesh networking is important. And I'll talk about this again in the context of the smart home, but I think this is applicable in many industrial settings as well, is that a lot of, even cellular cases, but especially Wi-Fi installations, follow a single point of failure hub and spoke model. This is the core limitation of Wi-Fi is twofold. One is that when a device actually can't reach the router, it is a useless dead device. It can't actually be a part of that network. Now we tend to install access points to create redundancy in a Wi-Fi network, to give it more scale, to give it more breadth for devices to access. But that doesn't solve the second problem of Wi-Fi, and that is that if your router catches on fire, or goes offline in some other way, every single device on the network loses its IP address. And when a device loses its IP address, it loses its ability to communicate with other devices on the network. Not only was that router the device's connection to the open internet, but it was the only way that those devices could even remotely think to communicate with one another on the network as well. The mesh networking tries to solve this problem by introducing a different model. There is definitely still a connection to the internet. Oh yeah, thank you. There is still a connection to the open internet, but it's facilitated via a gateway device. That gateway manages the devices that are allowed to communicate with the internet, and it handles addressing of other devices on that local network as well. The one key difference is that these individual devices don't have publicly addressable IP addresses. They have their own local network IP addresses. They can actually communicate with one another. One of the benefits this provides us is that if one of your devices actually catches on fire, and then another device loses its connection to the gateway, that the network can actually self-heal, can find a way to continue to reroute messages through the gateway. Again, this is, for those of us that have been around for a while, I know some of you longer than I have, this is just peer-to-peer networking. This is not necessarily anything new, but a lot of this, when it comes to the state of the art in the IoT, we've lost some of this ethos because we have moved, we focused a lot on Wi-Fi connectivity, when this actually enables us a model that not only is more resilient to the local network, but is fundamentally more secure because these devices cannot be reached from the open internet. They don't have public IP addresses. It's much harder for a bad actor to make them an attack vector. So, the problem, however, is that implementing mesh networking yourself is hard. The same way, I mean, a lot of the problems that I've described in your mesh, you can actually do with Wi-Fi as well, with intelligent network design. That is also quite difficult. Mesh networking and doing a lot of this yourself requires you to manage and roll your own security and encryption. Figure out how you want to do local routing on the network. Figure out how you want to handle local communication over stacks like UDP or TCP, etc. How you're going to deal with radio support, for Bluetooth, Wi-Fi, etc. Dealing with failover, routing, network management. All of those are things that you have to do yourself if you are theoretically wanting to approach mesh networking, but you don't have hardware that's necessarily capable of supporting it. Then thankfully, for us as implementers, it's not on us to figure out how to do mesh networking ourselves. There are mesh standards out there today, and there are newer ones that are coming along. One of the ones, the one that I'm going to talk mostly about today, was an effort that was actually pioneered by Nest and stemmed from them attempting to solve a real-world problem, which is why this is interesting to Particle. Now, I know we're all familiar with Nest. Nest started their life as a company that made smart thermostats. From an IoT standpoint, from a smart home standpoint, this was an easy problem to solve because you had a device that was connected to Wi-Fi and connected to mains power. It's easy. You hook it into your wall, connect it to power, no big deal. But when they wanted to move into smart thermostats, they actually had a new problem. This wasn't just a new device, but it was a device that probably shouldn't be on Wi-Fi, because smoke detectors tend to run off of batteries, not run on mains power. And when you run, some run on mains power, but a lot of smoke detectors need to run on batteries. And so therefore Wi-Fi is kind of a terrible option if you're trying to run on battery power over a long period of time. In addition to that, I mentioned earlier one of the key weaknesses of Wi-Fi is that when the access point goes down, the network loses its ability to communicate. This is a safety product, not a convenience product, and so Nest had a different problem of needing to make sure that these devices were network resilient. they actually took a look at Wi-Fi and decided because of power and because of that weakness they needed to go in a different direction. They looked at Bluetooth. They couldn't use Bluetooth because Bluetooth is point-to-point addressable or point-to-point communication mechanism, and they needed something where smoke detectors could actually broadcast messages to every device on the network. So, this is Nest, a part of Google. They basically created their own mechanism for doing this, and they basically created a networking stack called Thread, an 802.15.4 standard that they built into their devices, and that's the mechanism by which the Nest Protect thermostats and even newer Nest thermostats communicate with other devices on the network. Now, thankfully, Google tends to be a relatively open company in many ways, so they actually took the Thread specification. I know, not completely, but in this case, they actually did take the Thread specification. They contributed it to the community, and they formed a working group called the Thread Group. So the Thread Group's mission is basically to take the open source implementation of OpenThread and to make it a technology that's not just useful in a smart home context, or not just useful among Google and Nest created products, but among any vendor's product, any radio that wants to adopt that technology and use that networking stack. It's an open source spec. There's open source code to actually run the Thread protocols on device firmware. Particle is actually a member of this working group, along with many other companies from silicon vendors to commercial vendors as well. Yeah?
Is it a physical layer or a logical layer?
So there is a physical layer and a logical layer. Actually, the physical layer, there's both. So there's a device OS firmware piece, but there actually is a, I'll talk about the physical layer in a second as well. So really, simply put, Thread is just a low-power networking protocol. That's all it is. It's designed, and the reason why Particle has picked up on Thread, and it's interesting to us, because it solves the kind of use cases that our customers were looking for. When you're running Wi-Fi or cellular, it's much harder to have sleepy devices that run off of batteries. It's much harder to have devices that can sleep for long periods of time without causing an issue on your network, right? And so Thread solves this problem of not only being able to create wireless personal area networks, but enabling you to avoid single points of failure in a network, giving the ability to actually use in concert with Wi-Fi, cellular, and Bluetooth, so it's not a replacement for these technologies, but a way to actually create cheaper, more resilient networks. And because it uses IPv6, it actually allows us to do it. It actually gives you the ability to scale the network out quite easily without worrying about address limitations. Now, on the physical side, OpenThread will certify components created by silicon vendors. So there's several that are notable. If you go to OpenThread's website, I think it's openthread.org. If you go to their website, you can actually see a ton of different vendors that have implemented these Thread certified radios. But the ones that you would expect to see on this list are here. ARM has an OS version, D-Link, Nordic, NXP, Scilabs have all their devices. Particle actually uses the Nordic Semiconductor NRF52840. This is an interesting device because it actually handles, their device can handle Wi-Fi, cellular, and Bluetooth low energy. It basically handles communication without interference, on a single radio, and it's actually really neat. So that is the hardware side of what we have done with Thread, and then beyond that, there actually is a stack on top of that that I'll talk about in a second. But the whole reason that we went down this path is because compared to Wi-Fi or cellular, Mesh provides device connectivity at a lower cost with a lot of the same features and capabilities, which is, again, what a lot of our customers are doing. We're having customers coming to us and saying, we need to build an IoT solution. We don't want everything to have a Wi-Fi chip or a cellular radio. Cellular is twice as expensive as Wi-Fi. Wi-Fi in and of itself, we don't need it for all of our devices. Why are we paying for one of these radios on all of our devices? Mesh gives you the ability to have that connectivity to the internet in gateways in the right places, but to have cheaper devices that actually function as routers on the network, that function as end nodes on the network as well. Mesh networks also get stronger as you add more devices because you have the ability to, as I showed earlier, add resiliency to those. Now, I'm not going to pretend that OpenThread is the first implementation of a mesh networking standard. There are others out there. Some of these are more popular in the context of the smart home, and I treat LoRa as a bit of a mesh networking standard as well because I think it solves some interesting use cases at larger distances than Z-Wave and Zigbee do. And Thread is not the end-all be-all. One thing that I will mention that's interesting to particle especially is the thread is an open standard, as is Zigbee. And the thread group right now is working on Zigbee and open thread interoperability. So you would have the ability either in a smart home context or an industrial context to use both Zigbee and thread together on a single network without worrying about a lock-in on a single standard. Because this is another one of the areas where the IoT is not struggling, but where a challenge that we need to overcome is the proliferation of standards, especially vendor-specific standards that are pitched as the end-all be-all. So I'm really happy to see that Zigbee and the thread groups are working together. And I think thread is the kind of thing you can also use with LoRa as your edge devices or as your gateway devices that allow connectivity over longer distances. Because as you'll see, LoRa can handle an operating range that's much higher than any other standard that's standard out there today.
Actually closer to 10 miles.
Is it closer to 10 miles? Okay. Yeah. Which is fantastic. Again, we're talking 10 miles versus 230, so not 10 miles versus like 35 or 100 feet. Yeah. So, if you're wanting to implement the software, the firmware side of OpenThread yourself, this is what the thread group will give you. They'll say, hey, great, you want to build a thread network with our devices, our silicon? Here you go. Here's your block diagram of all the things that you need to do. Everything from dealing with platform drivers to handling MAC addressing for 802.15.4 devices, forwarding on mesh, 6 low WPAN header compression, all the way up to dealing with APIs, routing, OAP, UDP, it's alphabet soup. Building OpenThread into your own solutions is really a lot more complicated than just choosing a piece of silicon from a vendor. You can buy a dev kit, and actually if you're looking at a mesh networking protocol or mesh in general, I highly recommend buying a dev kit from Nordic. They have an NRF52840 dev kit you can get on DigiKey. It's like 30 or 40 bucks. It's fun to play with, prototype. I mentioned Scilab's Mighty Gecko is another dev kit that's worth checking out because it's important to see sort of what's behind the covers. But ultimately, if you want to implement OpenThread yourself, this is what you're signing up for: buying a dev kit, installing their software stack, and anybody that's ever installed a embedded device software toolchain on your computer knows that you feel like you probably need to get a new computer after you've gone through that exercise of trying to get everything actually working. Manually setting up and configuring routers, configuring end devices, implementing UDP-based messaging between devices. This is what you're signing up for if you're implementing mesh networking, even using one of these stacks. And this is why Particle exists, which leads me sort of to the third part of the story. We started with the goal of making Wi-Fi easy for developers and companies getting into IoT. We extended into making cellular connectivity easy for developers getting into IoT. And we want to extend that to mesh networking as well, because ultimately, my personal goal, this is not Particle's goal, my personal goal is that developers never actually have to see this block diagram after I show it the first time, because we want to make doing mesh networking via prototyping or production as easy as powering up a device, as easy as opening up a mobile app or opening up a command line interface to provision that device, or using a console to provision a fleet of devices, and then ultimately facilitating communication between devices via simple to use but extensible APIs. And there's really three pieces, the three ways that we have focused on trying to make mesh networking easy. And that is through mesh-enabled hardware that's pre-configured with OpenThread. So all of our devices are running the latest versions of OpenThread. They're using the NRF52840 chips, and they are ready to go out of the box. Simple assignment based on device type and location. So when you're building a mesh network, there is a little bit you need to know about device roles, and I'll talk about that in a few minutes. But when it comes to setting up your first mesh network, you don't need to know a lot of those things. You can turn on devices, add them to networks, and a lot of the determination of what role devices have in the network happens automatically at the firmware level. We make a lot of those decisions on behalf of developers so that it's easy just to get rolling. And then finally, secure local configuration between devices at the API level. You don't have to understand UDP or implement UDP messaging yourself to do multicast broadcasting between devices. You can use simple APIs. So a little bit more about our devices. I mentioned already, the Argon and the Boron are the the gateway devices, the devices that backhaul data to the cloud, the devices that facilitate connectivity into the local network if you have a desire to do so. The Argon is a Wi-Fi device, the Boron is LTE Cat 1. And then the Xenon is the mesh-only devices. These are obviously the cheapest devices, the devices that make up most of the backbone of the mesh network. All three of these devices have mesh capability between them, and they all have the exact same Nordic SoC on them. So they work really quite compatibly well between one another. They can all run the same firmware if needed, but obviously the gateways maybe, and a lot of the actual network management capabilities are baked into the device OS firmware that runs on those devices. They don't need to be written in user firmware in order for those devices to actually function. And there are three kinds of roles in a mesh network, and the way that we label them in the particle mesh context is a gateway. I've been used that term a couple of times. This is your only device. In this context, there's just a single device that has a connection to the network, to the internet. Your gateway device is the device that has a connection to the internet, that understands the topology of the network and the kinds of devices that are on it, and that can route messages from devices to the internet and messages from the internet back to devices. You have repeaters. And this is an important question. Yeah, go ahead.
So in your earlier example, you talked about when the Wi-Fi router goes down, you lose the internet connectivity to all the edge devices. In this example, though, if your gateway goes down, you still lose connectivity. I mean, because the devices can communicate amongst themselves, but they lose the internet.
You still lose internet connectivity. Yes, but you don't lose local network connectivity.
You have topography where you use a multiple gateway protocol.
You don't need to. So actually, that was a bit the point I was about to get to here. An important thing in the way that we've implemented particle mesh, and this is how OpenThread does it as well, is that the gateway is not the only device that understands the topology of the network or has the ability to even provision new devices on the network. Repeaters can actually function as joiner devices as well.
Okay.
So your gateway, even though it's the only device that has a connection to the network, it's not the only device that has a responsibility for defining the state of the network and managing devices on it. So a repeater device can actually bring other end devices on, even if the gateway is down.
Does it automatically sense if the gateway is in trouble? Does it take that?
Absolutely. So So role changes in promotion, like promoting certain devices from repeaters to the way that that's referred to, and this is the way that OpenThread refers to that is a leader device, whereas this is referred to as a border router device.
Absolutely,
right, yeah. So a leader device, if a leader device changes, the network knows how to automatically promote another leader based on their position or based on their role in the network, and that all happens transparently.
So then they just follow the leader.
So then they just follow the leader, yeah.
Go ahead. No.
So one of the questions that I had is, like, we work with Apache NiFi, for example, and one of the things I liked about it is that it has, like, say for example some network goes down, it has mechanisms in place to kind of store that data intermediate, and then it acts as a buffer for quite some time. Especially when you want to, like, know, I've modified the data this way, I've updated this way, data this way. It keeps track of all of that. So, so is there something? Is it a part of this? I'm trying to connect the dots between.
It's not a built-in part, but this actually enables that. It enables you to implement something like that more easily than if you were doing Wi-Fi only on a local network. In that case, in a Wi-Fi scenario, or even cellular, in some cases, cellular is obviously a bit more resilient. Every device would be responsible for storing their own local data if the network is down and then forwarding that on. You could have a scenario where the gateway may still be up, but the open internet connection is down because the router is down, so the gateway could still be functioning. Or you have other devices on the network that have a connection to some sort of storage device on the network that can actually handle local logging, local management of the data before it actually gets called back when the connection comes back up. So you would be implementing that piece of it yourself, the actually store and forward piece, but it's easier to do in this sort of a network scenario, I think. Good question?
Yeah, my question was along the same lines that, so okay, based on what you said, we still have data, but we cannot do analytics on the cloud side on the data. So then, do we store it anywhere? But I guess.
Yeah, you absolutely would. That, and not so much relevant to here, but that does lead to some interesting conversations around actually that level of edge computing. There's been a whole lot more, as our embedded microcontrollers and SoCs have gotten a whole lot more powerful over the last 5 or 6 years. There are cases where running not actually training models, but actually running training models on the edge on devices is more easy than it was 5 or 6 years ago, and happening more and more. So even if you were storing that data local there, in the next couple of years, it would be a lot easier to even run those models against the data that's local in the network. So you're not even backhauling everything if you don't need to. Yeah.
I have a question. Are there people also doing stuff with the backup connection? Let's say you've got normally a router, but then you can have a cellular connection out.
Yeah, that's absolutely right. I have a slide on this in a couple of minutes, but you absolutely can. Another piece of this model that's useful is the gateway doesn't have to be, your Wi-Fi gateway doesn't have to be only single point of failure. You can have Wi-Fi and cellular. You can have a Wi-Fi and Ethernet device as well, and that actually is a really common use case. We have customers that are using an Ethernet connection as their primary, but cellular as a backup. Right? Yeah. I don't remember the order. Next question. Back to the room.
Can you have multiple gateways?
Yeah, you can. Absolutely can. Yeah, you can. So in this case, I have a single gateway that's just running on an LTE device, but I can have LTE Wi-Fi, LTE Ethernet, Wi-Fi and Ethernet. So I can have multiple Wi-Fis. Yeah. You can have as many gateways as you want.
But how many active at a time?
They can both be active at a time. Yeah, yeah. And then the network, and again, both of those can actually facilitate passing backhauling data to the cloud. And based on which one is receiving messages from routers or from edge nodes, they will decide to be the one that actually sends the messages out.
What's the distance between gateways and repeaters, no repeaters?
It somewhat depends on network design. I mean, we've actually have customers that are actively testing this now, so it's a great question I'll share. The question was about distance between nodes.
Because the theoretical limit of Wi-Fi is 350 meters
right.
At full power.
Right. We had a customer that's been testing this really actively, and what he observed, if you can attach antennas to each of these devices, and he did this. So with a PCB antenna on both the gateway and on an edge device, he observed in a business setting 50 meters, about 150 feet. In a home setting, he was observing twice that, so 100 meters, and then in a line of sight test, he got 500 meters. So quite a bit more than Wi-Fi, quite a bit more than Zigbee and Z-Wave, but not nearly to where Laura can get at this point.
Well, yeah, but the other different applications, right?
Yeah, absolutely. Did you have another question?
Yes, I was wondering, so then earlier you mentioned that one of the great advantage of the mesh technology is that if the gateway catches on fire, it's still okay for the network, and they can also sense the repeater and then the other nodes that, okay, my gateway is down. Mm-hmm. So that being said, why can't they detect and then they enable their cellular or Wi-Fi hardware on it and then be gateway in itself?
So that level, that's built in today with the particle mesh hardware, is that if you have a second gateway on the network, and it has a Wi-Fi or cellular radio, you have a couple of ways to do it. One is you can leave that radio on, and it just functions as a gateway. So if you lose one, the other one is still routing messages, and everything is fine. But the other is you can easily in software detect if that gateway has lost its connection, and then turn the Wi-Fi radio on, and then start back on it. So you can intervene on your own. The key difference is that because these devices don't have those radios, they are cheaper. Because of that, they're easier to add more of these devices to the network. But if you want that level of resilience, you need to have more devices that have that Wi-Fi or cellular radio on them. Question there? Go ahead. Oh, yeah.
So that's the networking layer that you're looking at, something slightly different layer where you're doing like all joint in, or another layer like
Can you repeat the question?
Yeah. So all join in is like above the networking layer, and it provides a messaging bus so that you can on top of the networking layer, but in a similar fashion.
So I have not looked at that specifically.
Because that's the other problem, right? You've got networking layer, but not any kind of application.
Yeah. So the question is, we've looked at this at the networking layer, but have we done anything to look at it sort of at the bus layer, the communication or transport layer? And I'll say where we are right now. And so a lot of the APIs that we baked into the device OS, if you haven't used particle devices before, there are two pieces of firmware that run on the devices. There's what we call device OS firmware. That's the system firmware that does everything in providing GPIO access to the device, actually facilitating communication with the cloud and making sure the Wi-Fi connection is on or cellular connection is on. But it also provides a number of APIs that provide developer-friendly abstractions. So in our early generation hardware and even our current hardware, you can do publish and subscribe to messages between devices across different networks, publish messages to the cloud. You You can expose functions to the cloud that can then actually turn on actuators on devices. You can expose sensor data to the cloud to be read elsewhere. All of that's been in the device OS for a while. One of the things that we've added for the new generation hardware is UDP-based messaging via mesh, publish, and subscribe. That's the extent of what we've done so far.
I was going to say, most of the other companies that are in this use all join in or some other transport layer, application layer messaging scheme.
Yeah.
And that's just an extension bus on top of that.
On top of that, yeah. I think that's an interesting thing. I need to take a note of that and ask my engineers if they've actually experienced it. Yeah, absolutely.
Last question for me. If you have Wi-Fi and you have cellular, can you actually do traffic shaping? Because Wi-Fi inherently is coming off an Ethernet connection, which is not metered, and the cellular, of course, potentially you could have a metered cellular connection. Can you actually shape and prioritize?
So you actually to intervene on where the network traffic goes if you have multiple gateways.
Yes.
Yeah, you absolutely can. That's a user firmware capability. Obviously, you would be at least in what we have today. But I think that is something we're looking into in terms of allowing you to define prioritization based on the type of radio that's in there. We would have a lot of customers who would use Wi-Fi first and always, unless Wi-Fi is down, and then use cellular.
Right, as backup.
Yeah, as only a backup, but there are definitely cases where you may want to use a mixture of both.
Right.
So no true software behind that.
Yeah, we probably should let them flip to the next bill on the slide, right?
Yeah, one question. I know that the network mesh establishes itself automatically, but what if some of those are moving relative to the others? How difficult is it to reestablish the network if it's constantly moving physically?
So the question is how difficult, if there are nodes on the network that are moving, their position in the network is changing, how does the network manage that, or how difficult is it to reestablish a connection? The answer is twofold. One is there's always a caveat that network design is key in this type of a scenario, and thinking about the topology of the network physically and how most nodes are based on the actual environment that they're in, the RF environment, the physical environment, etc., will somewhat determine how many nodes you need or where they need to be positioned. But assuming that nodes have the ability to communicate with one another, the network will always reroute or self-heal based on how nodes are moving. So if a node goes completely out of range, then it's out of range. But if the node is in range and it moves from here to being more in range over here, that happens transparently. It happens automatically as devices are setting heartbeat checks and making sure that they're aware of what's my closest repeater. Because this is an important, the next build that I had here is basically, which is kind of makes sense, is you have your workhorse devices on the network are your endpoint devices, the devices that are sensing and actuating. They're the reason why you built this network in the first place. They will and will need to have connections either to a repeater or to a gateway. But you can also have devices that function as both. They may be connected to an endpoint, but because of their position in the network, they also function as a repeater. So they're not isolated roles. You can have gateways that function as end nodes, as end devices that are sensing as well. But all of this is somewhat dependent on where you position them. But assuming that there is a stable connection between two devices, even if that connection has changed, the network is able to reroute and figure their way out to the gateway. So, and I mentioned earlier, a lot of what we have done in the developer side is designed to make, this is a relatively complex topic in mesh networking. It requires a lot of network design, a lot of thinking about what the network looks like. But when it comes to starting and prototyping with this, we have a lot of developers that just want it to be easy to get started. So our focus has been on making it very easy to get devices online. If you get a device from Particle today, pull it out of the box. Provisioning that device is done via Bluetooth with your phone, with an iOS or Android phone. That device is then online. If it's a Wi-Fi or cellular device, it becomes the gateway automatically. If it's a mesh device, it becomes a node in the network, and you can go nuts off to the races beyond it. Now, I mentioned publish and subscribe, and we have built APIs, UDP-based APIs for communication between devices. You can publish messages on the local network, subscribe to messages on the network. If anybody is interested later, I have some demos that I just did earlier this year because I was testing mesh publish and subscribe network latency, and I actually strung together a network of connected Christmas trees with NeoPixel strips that are connected to like 12-inch Christmas trees. And I was testing sending mesh pub-sub messages and then lighting up those strips and how quickly it would happen at the press of a button. And it's, according to my eye at least, it's pretty instantaneous. So these are low latency messages. The whole point is it's not publishing through a cloud and then back again. One of the big limitations of a lot of smart home technologies, and all of us know this, but a typical consumer doesn't quite understand, that when you have two connected devices in a network and I say, Alexa, turn on my light bulb, it goes up to the cloud and then back down into my house to do something that's 2 feet away. Mesh networking allows us to build networks that actually do communicate locally and don't require device clouds. But if you need a device cloud, if you need device management, there are still those capabilities. So Particle, from the early days, has provided a device cloud for managing devices, individual devices, for managing fleets of devices and the firmware on those fleets of devices. And that's been an important part of our DNA and continues to be even in the context of mesh networking.
Do you know how long?
Sub-millisecond delay, yeah. I have not yet, so my early testing has been devices closely grouped together to see if it worked, and then I'm going to slowly, yeah, absolutely. Yeah. And so, just to underscore as I wrap up for the next couple of minutes, the whole reason that we did all of this is not to be a replacement to existing Wi-Fi or cellular solutions, but to make existing IoT installations smarter. One of the reasons, or one of the early examples that we've given to a lot of our customers that has resonated, is if you have an existing setup, whether it's in a home or on an industrial floor, with an existing setup could be something like a flood detector, a smart water meter, and a pump controller. You can have a case where your actual meter is connected to the Ethernet. Mesh devices, even if there's a local network of devices, they can actually still publish messages to the cloud. So a water meter can still publish its health and say, hey, it's dry here, everything's fine. That's getting back home to the cloud, no big deal. You can also still, in the context of a mesh network, have an end device like a pump controller that can be controlled from the cloud to turn that pump on or off. That all works just as our solutions do today. And to underscore, I think we all get it at this point, but the whole point of mesh and why it really matters in a lot of cases is devices can communicate without a network connection. So if that Ethernet connection goes down, if the Wi-Fi connection dies, you still have the ability where a pump controller or a water meter can trigger, if it detects water, can actually trigger that pump controller to turn off or turn on to pump water out of a space. It's an important part of why we did this. And a lot of, again, why we try to do this is making it easy to do publish and subscribe between local devices. So to wrap up, I'll just share a couple of different examples of where the types of networks that mesh networking enables. There's some questions around this already. I'll cover them again really briefly. A lot of people will start with this sort of case where you've got a single gateway and multiple repeaters and endpoints. You may have every device on this network that's connected as an end device, and based on their location, they're just routing messaging. But you have a single connection or a single gateway to the cloud. But you can also have dual gateways, multiple gateways that connect to multiple local devices. And again, the network will manage itself which end device or which router assigns its data into which device. And there can be many cases too where if you're using, this is the wrong one. Yeah, so if you're using Wi-Fi as your primary and cellular as your backup, these two devices, depending on where they are, in many cases they would be grouped pretty closely together, can also be connected to one another. And so Wi-Fi becomes the predominant means of communicating with the cloud only, and cellular is only used if the Wi-Fi network is down. Again, those things are meant to be very transparent. I'll bring the slide back up again because this is where Gartner thinks that we are today. This is where I think, yeah, go ahead.
In the previous slide, can you do load balancing when you're connecting to Wi-Fi, or because going through one device you just create a bottleneck, right? According to the data.
Yeah, obviously it depends on how much data you're actually streaming back. I mean, it would have to be a ton. You can, in intelligent routing, there is some degree of intelligent routing baked in, and we anticipate, though it's not available today, to actually expose some APIs to handle some form of load balancing and routing between them. It's not built in today. It's not, the APIs are not there today, we're just relying on what's built in the device. Yeah. So I have a few more minutes for a few more questions, but as I wrap up, I just want to share.
Do you have any fielded deployments right now, or is this also new that you haven't sold?
So yeah, we have sold it. So the products we announced in February, we took pre-orders for prototyping that we just started shipping in October. So people are actually in the field working with them, experimenting with them right now. So we don't have any actual field, any like deployed use cases just yet.
Okay.
Yeah.
But question, in all of your diagrams, you show a mailbox and a fridge and so on and so forth. So how easy or how difficult is it to make a pre-existing device, a mesh-enabled device that works with your technology?
Yeah, good question. So how easy is it to make a pre-existing device mesh-enabled? It depends mightily on the device. I wouldn't try to connect my fridge with mesh because I don't want to open it up and break it and void the warranty. So they are a bit sort of tongue-in-cheek examples in some of those slides. But when it comes to connecting an existing embedded microcontroller, that's as easy as just wiring up a connection via serial, via I2C, just an existing bus capable on that device. So I've done this in a couple of cases. I have an Adafruit device that runs AT-SAMD51. If you're familiar with that, and it's another microcontroller. It doesn't have mesh built in, but it does have a serial port connection. So I wire that up to a Xenon, and then I can actually do serial communication between those two devices, and then from the Xenon mesh publish messages to the network. So I'm proxying communication. You can actually meshify sort of non-mesh devices, even those those production grade devices. But you can also have devices that have multiple if you're building a custom PCB, design devices that have multiple microcontrollers to serve those purposes as well.
Just a follow-up question.
Yeah.
So are you trying to move towards a scenario where you just have a USB plug that into your device and it turns the device into a particle mesh device?
That's a cool idea. So are we trying to get to a scenario where you can just plug a device in via USB or something and it turns the device into a mesh device? That is not something that we've talked about. I love the idea. I mean, it's actually kind of cool. You just kind of meshify anything. But yeah, I mean, ultimately, we'll have to see. We'll have to see where things go.
So is this technology, obviously, when there's a mesh of devices, it makes sense? Does it make sense at all when you have like something like a truck that you have put in, or for things like that, it's just better to go with your cellular connectivity?
Yeah, so there are definitely still cases where, our current generation devices, the Photon, Wi-Fi, and the Electron Cellular, are still available, and we still have customers that are actively using those and planning production deployments with them. Because there are cases where you're not building a network of interconnected devices, so you can still use those, and in the case where you've got you're monitoring systems in a truck or sort of a single location, everything's connected to one microcontroller, that may be an ideal use case. But you can also use these devices in standalone mode. So you can use the Boron as a cellular-only device, and it doesn't have to have a mesh network of devices. And then if you ever get to that point where you want to actually add additional nodes to it, you could do that at that point. So you can sort of future-proof it a bit, but still have a network of one in the short term.
I'm just curious, what sort of price of a Photon in quantity thousand?
So the price of the current Wi-Fi devices? So for those in quantities, we sell there's two versions of the Photon in like module size, so not the actual dev kit. Either with or without a PCB antenna, the P0 or the P1, and we sell them in manufacturing reels. And in quantities of 1,000, they are less than $10 a module. That's as specific as I can get without.
I said they were like 15 in quantity one, $16.
The Photon is about $20 in quantity one, and the P0 and P1 are
We've got a sale right now at 15.20.
15.20
on sale.
Yeah. Okay.
What would you do for me?
I would email you somebody in the sales team that can answer those questions. Oh no, I love
Did I not
this.
say I was the supreme benevolent?
But that's awesome because I just bought some feathers, and they're over $30.
Oh yeah. And actually, I didn't mention this here, but all of the particle devices are all Adafruit Feather compatible. So if you have existing Feather form factor stuff, it all just plugs in.
What were you
It works great.
Yeah.
Dude.
I'm glad I came this morning.
Yeah.
You mentioned about ARM Trust Zone and Secure Boot. Are the firmware updates publishable?
Yes. You mean publishable as in to a fleet of devices?
Yeah.
Yeah. So I didn't talk about this specifically, but we handle firmware updates by default over the air. So they actually happen from our device cloud securely on the devices. So if you're managing a fleet of devices, you can push OTA updates to your entire fleet of devices at once.
Nobody will probably thank you, but thank you.
Oh, well, thank you for thanking us. I'll pass that along. That's great.
What's your most successful deployment to date? What type of device?
It's under NDA and I can't share. Our most successful is an NDA customer that they use an asset tracker to manage small two-wheel devices. That's
You mean the same one that just got thrown out of Frisco?
No, not yet. We actually, one of the ones that I like to share because it's an interesting one is Jacuzzi. Yeah, so Jacuzzi has it's a small fleet right now, but Jacuzzi has actually started working with the particle photon, the P0. So they're using it at scale. What they've done is they've actually built the product in all their newer smart hot tubs. And you think, okay, well, yeah, so the first world consumer can turn their hot tub on from inside the comfort of their home. And while that is something that consumers will do, it's not really the end game for them. It's not the ideal use case. As with most of us, the end game is preventative maintenance. They want to actually get sensor data on those hot tubs so that over time they can fix problems before they happen. So they can actually start to know over time when a pump is going to go out, when there's an issue with a motor, or they can actually get you, on a subscription service for chemicals, so that you can keep your hot tub alive and healthy for a longer period of time. So I know that I'm out of time. I'm happy to answer questions later, but I'm really happy to have had an opportunity to chat with you all this morning. So,
You're welcome.